Hello and welcome everybody to today's live code along. My name is Senne, the Workspace Architect intern here at DataCamp. First of all, thank you for attending the 6th Workspace live code along. A huge thank you as well to our speaker, Lis, who together with DataCamp and especially all of you made this event possible. During the session, we will show you how you can use a machine learning tool called XGBoost in DataCamp Workspace. You will learn to create, evaluate, and tune XGBoost models efficiently. I have posted, and I'll post it again, a link to the template we will be using in the chat. So if you want to code along, be sure to open that link. It will automatically open up a workspace for you. So next slide, please. A little bit about DataCamp itself. Our mission statement is to democratize data science education and make data literacy accessible to millions of people and businesses around the world through our learning platforms and now also through our DataCamp workspace, certification, and events such as this live code along. Our speaker today is Lis Sulmont. She is the Workspace Architect here at DataCamp. Lis holds a master's degree in computer science from McGill University. She is passionate about teaching all things related to data and improving the accessibility of these topics. She worked on the DataCamp curriculum for over 2 years. During this period, she instructed several courses for Tableau and Power BI, and also for Everyone courses. So now she is the Workspace Architect at DataCamp, where she will be focusing on building out the template and dataset library. Today's live code along is divided into several parts. In each part, Lis will show and go over several machine learning techniques in XGBoost. Throughout the session, there will be 2 Q&As, so feel free to leave your questions in the chat. I will post the template link once more so you can open it up and then you get access to the workspace that Lis will go through. With that being said, I wish you all a very learnful live code along, and over to you, Lis.
Hey everyone, thanks for joining. So before we get started and start coding in a workspace, I first want to go over what gradient boosting is, as that's what we'll be using today. So when thinking about gradient boosting, there are really 2 main components that help us break down and understand the algorithm. The first one is decision trees, and the second is boosting. So let's first go over decision trees really quickly. Decision trees is a machine learning technique that uses tree structures. At each node, the data is split into pieces based on the value of a feature, and the algorithm finds the split by finding the best information gain possible. So a decision tree is composed of a series of binary questions, meaning there's only yes or no answer, and it's constructed iteratively, one decision at a time until a stopping criteria is met, which we'll set during the code along. And then the leaf node has a single decision at the end. It can be used for regression classification problems, and also decision trees are often referred to as cart, classification, and regression trees. So if you've ever seen cart, it's a type of decision tree, and XGBoost, the gradient boosting library that we'll be using, uses cart trees. So here's an example of a decision tree. I completely made this up. What we're trying to see is if it's going to snow tomorrow. We see that each node has a question. So the first question is it between May and September? So if it is yes, so basically if it is a summer month here, I'm based in New York, that means no, it probably won't snow. But if we say no, it is one of the more wintry months, we get different questions like, did it snow today? Is the humidity less than 30%? And then is the temperature less than -2 Celsius, for example? So you'll see that these have a no yes answer to will it snow, but along with that, you get a prediction score. So usually the default threshold for a decision tree is 0.5. Meaning that if the prediction score is less than half, then the answer is no. But if it's greater than 0.5, then it's yes. The threshold is something you can change, but usually 0.5 works for binary problems. going over some tree terminology that will come up. So as I said, leaf nodes contain the decision. They are nodes that have no children, so they're all the blue ones here, and they lead to no other nodes. So once you reach a leaf node, a decision is outputted as well as the prediction score. The root node is the top of the tree, and then we also have tree depth. And that's the longest path from the root node to a leaf node. So we see here we have 1, 2, 3 paths. So the tree depth here is 3, because that is the longest path in the tree. You'll see that this is a parameter that we'll play with during the code along. It's an important one, and we can use it as a stopping criteria. So now, what is boosting? Boosting is an ensemble method. The idea here is that you convert many weak learners into a strong learner. And a weak learner is defined as a model that's slightly better than chance. So decision trees are great weak learners. So boosting, specifically gradient boosting, tries to leverage decision trees as weak learners and combines a bunch of decision trees to come up with a solid prediction. So boosting is accomplished by sequentially training weak learners. This may sound similar to bagging. Bagging is another big ensemble method. So bagging, instead of sequentially training weak learners, bagging, you train weak learners in parallel, and then you average the prediction, or you vote on what the final prediction will be. So here's just a visual summing up what gradient boosting is. We have a number of decision trees, which we'll be able to set when we code. And the idea is that the next decision tree is trying to correct the mistake of the previous learner. So gradient boosting tries to fit the new learner to the residual errors made by the previous learner. I won't go too much into math and how that's optimized, but residual errors defined as the difference between the observed value and the estimated value. This maybe sounds familiar if you know ADA boosting. The difference between ADA boost and gradient boosting is that in ADA boosting, you're changing the weights of every incorrect classified observation. It's also an interesting method, but here in gradient boosting, we're really trying to correct the preceding tree's errors. So we'll be using the XGBoost library. This is probably the most popular Python library for implementing gradient boosting. It's known to have really good memory efficiency. And when we use XGBoost, you'll see that weak learners are referred to as boosters. So weak learners will also be referred to as base learners or boosters in this context. There are many types of weak learners you can pick. Decision trees are the most common. That's what we'll be focusing on. So we'll be setting our booster as GB tree, which sets a decision tree. Another popular option is linear regression, just for your knowledge, and you can always set that by setting booster as GB linear, excuse me. So I'm gonna go ahead and open up the workspace and we can get coding. Okay, so before we get started, let's talk about the data set, what we're trying to predict. We have a hotels booking data set originally from this article right here. I've completely pre-processed this data set even further than the source link here, just so that it's ready for us to use. I dropped irrelevant columns. I've done one-hot encoding. So we don't have to worry too much here about cleaning our data. Let's just do some basic exploration first so that we understand what we're doing. In terms of the data itself, our target is going to be is canceled. So we're trying to predict whether a booking will be canceled or not based on the booking's characteristics. So this is useful, especially if you work in travel industry or hotel industry and you're trying to maybe figure out how many bookings you should have. Overbooking is common because it is common for bookings to go canceled. So just to make sure that you're at full capacity when possible. So our target is canceled, and then we have a bunch of features here, from lead time to number of stay, number of children, adults, repeat guests, the types of meal they requested, if it's a resort, booked by agent. So it's a very rich data set here. I'll let you peruse this data dictionary on your own, but we see here that we have a lot to work from. All right, So to get started, let's import our libraries. If you're unfamiliar with Jupyter Notebook, you can run a cell by simply pressing this button right here, or you can also do Shift Enter. That's what I'll be doing. So we've imported pandas as PD, XGBoost library. XGBoost is usually nicknamed XGB, so we'll be using XGB throughout this notebook, and NumPy as well, as that's just useful for basic arithmetic. So let's read in the data set. If you go to the editor, you'll see the data set is within this directory. It's called hotel bookings clean.csv. So I'll just collapse that so we have more room to see the code. And let's read it into a data frame called bookings. So we'll use read CSV here, and then hotel bookings underscore clean.csv. And then let's list out our columns just using .info and see what we have. All right, so is canceled is the first column as expected, and we see all the columns pointed out in the data dictionary, so we know we have the right data set. It has 53 columns and 119,000 rows about. All data types are numeric. We can see that here, and there are quite a few binary variables as well. We can look closer at the column distributions by doing bookings.describe. I personally like this. I find this an efficient way to just see what the data is about. So we see there are no empty values because I had cleaned this already. We see they all have 119 and 210,000 rows. Then what's useful here is you can see the mean and standard deviation, the percentiles for each value. Again, note some are binary, like is canceled, so it's not going to be as interesting to read. But this makes sense. For example, arrival date month is 6.5. There are 12 months, so it makes sense that that's around 6. Week is 27. There are 52 weeks in a year. So this is looking normal. We see that the average booking has 1.8 adults, so around 2. So this is just useful to get a sense of the data and distribution. All right, so we're really focused on is canceled. Let's see how many are canceled and not, because if only a few bookings are canceled, then that will definitely affect our machine learning method here. Okay, so I'm calling the is canceled column, and then I'm counting the values. So if you remember, binary variables are either 0 or 1. So we're just counting here, and then we can plot this easily by using .plot, and we can make a nice bar chart. Okay, so we see here 0 means not canceled. So most bookings are not canceled, but definitely a strong portion of the data set is canceled. This is important because if we had only, a few rows canceled, then that means we would really have to change our machine learning method because we would just not have as many examples of canceled bookings. We can get an exact percentage, again, by calling that column is canceled and value counts again. So this is just going to count the number of times. And then do bookings is canceled dot count. And then we're going to times that by 100 so we get a nice percentage. So 62%, about 63% actually are not canceled, while 37 are canceled. So again, this is a nice majority here, so we don't have to worry too much about not having enough examples of canceled bookings. All right, so as I said, we're not going to focus too much on data exploration or data cleaning since I've done that already. We're going to go ahead and just split our data. So we need X and Y, which is basically X are features and Y what we're trying to predict. So Y is simply going to be the canceled column, while X is going to be everything else. So we can do this easily in one line by doing bookings.iloc. So here we're defining X, and that's going to be all the rows and then all the columns but the first one. Remember, in computer science, coding in general, we start at 0, so 1 here equals this, means the second column onwards. And then when we define y, it's going to be very similar. Again, we use iloc. We can do all the rows, but simply the first column. And then we have defined that, and we're going to use this continuously throughout the notebook. All right, so let's do our first XGBoost classifier. As I said, XGBoost is its own library. It's available in R as well as Julia and other languages. But what's really nice about the Python version is that it has a scikit-learn API. If you've done machine learning in Python, you've probably used scikit-learn. So it's really nice because we can use a lot of the functions that we usually use in scikit-learn when doing machine learning on the XGBoost library. So I'm talking functions like predict and fit, which you've probably used if you've used scikit-learn before. So we'll do this by using the XGBoost.xgb classifier class. So that's XGBoost's classifier model. And we're going to start by getting a baseline accuracy for the rest of our work. And so that our results are reproducible, I'm going to consistently set the random state as 1, 2, 3. So that way you get the same results that I'm getting as we're going through this. And just note that if you change that random state, you're going to get different results than me. Okay, so to begin with, I've already imported sklearn, model selection, the train test split. Again, really nice that we can use scikit-learn functions within this XGBoost library. And I'll go ahead and define xtrain, xtest, ytrain, and ytest. And then we can go ahead and call train test split. And again, we'll call xy, the ones we defined earlier on. For test size, I'm going to do 3.33, so a third of the data set. And then again, random state is going to be 1, 2, 3. And then we can go ahead and instantiate a XG classifier. I'm going to call it XGB_CLF. This is common short nickname for classifiers. And then we can go ahead and call this class. And then what I want to do now is inspect the parameters. So if you're new to machine learning, one of the most important things is not just picking a model, but also understanding the parameters that come within a model and understanding how you can tune those to get better results, better predictions, as well as really avoiding overfitting, which is one of the biggest problems when developing machine learning models. So this get params basically just outputs all the parameters of the classifier model. This is nice just to see what you can customize and set. We're not going to go through all of them, but I want to highlight a few important ones, and we'll dig deeper into some of them as we go through this notebook. So the first thing I want to note is booster. Booster, as I said in the slides, that's another word for weak learner, base learner. It says none here, but the default is GB tree, which represents decision trees. So we want to keep that as decision trees. As I said, you can experiment with other weak learners, but we're going to stick with decision trees. Here, you'll notice the objective is binary logistic. So the objective function, also known as the loss function, quantifies how far off a prediction is from the actual results. So we want to minimize this as much as possible to have the smallest possible loss. Binary logistic is the default for classifiers, and it outputs the actual predicted probability of the positive case. In our case, that a booking is canceled. So here, that's when we use the threshold. If it's above 0.5 probability, let's say yes. If not, let's say no. So we're going to leave that as binary logistic. And then another important one is N estimators, which you can see here. It's currently set at 100. So N estimators is the number of gradient boosted trees we want in our model. It's equivalent to the number of boosting rounds. So as going back to this diagram, every tree that you add is another boosting round. So in this diagram, we have 4 boosting rounds. For our purposes, we don't want too many boosting rounds or our training will take too long. I don't want you guys to have to wait so long for results as we're doing this. So we're going to lower this from 100 to 10. But as I said, when you experiment at home, I highly suggest increasing that because it will most likely increase your performance. Then we have max depth, and this goes back to the tree depth shown in the slides. Max depth is the maximum tree depth allowed, because if you think about it, a decision tree can just keep going on and on until it runs out of features, but that will make it very prone to overfitting. So we don't want this too high. Similar to an estimators, the more we increase this, the longer our training period will be. So we're going to keep this at 3 right now. And then another one I want to point out is eval metric. This is another one you can play with on your own. This is the evaluation metric for validation data. So we're going to use error as defined by XGBoost documentation. This is a really helpful link that goes further into all those parameters we see here. And error is binary classification error rate. So it's probably what you expect, the number of wrong cases out of all the cases. Yeah, and then again here it talks about if it's larger than 0.5, it's going to be a positive instance. If it's lower, then it's going to be a negative instance. So we're going to go ahead and set the parameters as we've discussed here. You can do this easily by calling the model we instantiated, XGBCLF, and then use the set params function. And then we're going to go ahead and say n estimators equals 10. I'm going to copy this so I'm not rewriting the same thing. Max depth equals 3. Evaluation metric error. And then let's go ahead and fit it to the training set and see what our baseline accuracy is going to be. And then we can define preds as XGB CLF.predict X test. And then what I'm going to do here is also call the parameters again so we can see how they've changed. All right. So nothing is outputted yet in terms of accuracy. We're going to do that in Excel. But we can see here our booster is GB tree. What else did we change? And estimators is 10. Max depth is 3. So we've altered the default parameters. And we can go ahead and calculate accuracy. I'm going to call a function to do this later on, but I just want to show you guys how we calculated it. First, we want to get the sum of all the times we've accurately predicted the Y test. And then we're going to put that in a float so that we can divide it by the number of rows in our test data. Let's see if I forgot any parentheses. I don't think so. And then we can go ahead and print that. Okay, and we get a baseline accuracy of 80.62. That isn't bad, but I think we can improve it quite a bit, especially considering we're only doing 10 estimators, our max depth is 3, and we haven't touched a lot of these other parameters. Before we dig in too much into the other parameters, I want to talk about visualizing gradient boosting models. I think this is probably one of the biggest benefits of using gradient boosting. So we know, neural networks and a lot of deep learning models are super powerful and really great at predicting. But one downside of those models is that it's hard to interpret how we get certain results. And sometimes, especially in business use cases, we want to understand why we're predicting a certain outcome. And what's great about gradient boosting is because it uses decision trees, and decision trees are quite easy for us humans to understand. You know, a decision tree is basically a series of questions, and we can understand why a certain output was decided or why a certain decision was outputted. So gradient, the XGBoost library has this awesome function called plot importance, which plots feature importance, meaning how predictive each feature is for the target variable. So this will help us see which features are really high indicators of something going to be canceled, of a booking, that a booking will be canceled. So we can call this by just doing XGB plot importance. And then we'll call our baseline model XGB CLF. Oh, and sorry, before I run this code, I've imported matplotlib to plot this. And then this code is just simply to make it look nice on the notebook and not too big. You can change these if you want the outputted visualization to be a different size. So if we run this, oh, I have an error, CLF. If we run this, we get a graph of the F-score, so that's the feature importance, and then the top features. So we see one of the top features is lead time. I think that's defined as the time between the booking and the actual stay. So that's interesting. Maybe if something is booked way more in advance, it's less likely to be canceled. I'm just making that up, but it's interesting that it is an important feature. We also see customer type transient party. In the hotel industry, this has a specific definition. I think this is if they're really staying for one night, or if it's a business trip, it's not an extended stay. The data dictionary has more information on that. We see if they previously canceled, if it's non-refundable, we see other things. This is interesting, but what I want to note here is how do we define feature importance here? What are we looking at? So if we look at the documentation, there are actually 3 ways you can plot feature importance in gradient boosting. The first one is weight, which is the default, and that's the number of times a feature appears in a tree. So these features appear the most in the trees. I think we set it as 10 gradient, 10 and estimators. So out of the 10 trees, which ones showed up the most in a node? And there's also gain and cover. I want to talk about gain, and gain is the average gain of splits which use the feature. So gain essentially quantifies how much a feature contributes to improving accuracy. Not necessarily how much it appears, but how much it can split the data, essentially. So let's see how much it differs from weight. So we can go ahead and I'm just going to copy and paste this. Let's copy and paste this, but set the importance type as gain. All right, so we see here quite a different graph than the others. And we see that non-refund is way, way stronger in terms of importance when we're talking about gain than when we're talking about weight. It seems like they have similar features, but again, what the takeaway is here is that feature importance is subjective. You have to be careful on which metric you are using to define that. So make sure to really get the full picture on that. And the second is that the number of appearances a feature has on a tree is not necessarily correlated to how much gain it brings. So for example, as I said, there are quite a bit of binary variables in our feature set. And binary variables have less chance of appearing as many times as continuous variables, since there are only 2 outputs in binary variables. While on a continuous variable, you can say less than 5, less than 3, greater than 10, and so on. While binary variable, it's only, is it 0 or 1? So this will depend on what type of data you have. So just keep an eye out on that. But again, this is useful to understand more what's driving cancellations. Going back to interpretability of gradient boosting, what's really nice is you can actually plot the trees that are in your model. and that's using plot tree. So how that works is you call XGB.plotTree, and then we put in our model again, XGBCLF, and then we have to define num trees. So num trees indicates which tree you want to see. So for example, if we have set the n estimators to be 3, so 3 decision trees in our boosting rounds, then we can set the num trees parameters as 0, 1, or 2 to see the first, second, or third tree respectively. So if I want to see the first tree in our model, I can just set that as 0, and we can actually see the tree and how it's making decisions. So again, each node represents a binary question. There's only yes or no. And then in the leaf nodes, we have the output. So the output here is actually the raw score, and it's going to be converted to a probability at the end of training. Note this is the first tree. So for example, if we do the second tree, we'll get a totally different tree. So you can actually put this all together to see all your trees, or even just the last one, which will be 9 because we have 10 boosting rounds. Another good thing to know about this plot tree function is that you can plot left to right. Sometimes there's just too many branches, and you can do that simply by doing num trees equal 9, and then you use rank dir L left to right. Let's see, I have an error here. What is this error? Okay, I had a typo here. Yeah, so basically same tree, but just presented left to right. So just an aesthetic choice at that point. All right, so we're reached our first Q&A. So add any questions you have, and I'll go through them. So it seems we have one question. How does XGBoost fare when it comes to interpreting the impact of features on the target variable vis-a-vis algorithms based on linear combination, like logistic regression? Yeah, so I think this section shows it pretty well. You can really quantify the feature importance, and the interpretability for humans is pretty great here. We can see which features are important by different evaluation metrics, as well as really just understand why something is outputted the way it is. So we have another question. Does feature selection matter in XGBoost? Should we try to drop features or try different combinations of the features? Or would the decision trees take care of that? Great question. So I think in general, in machine learning, feature selection does matter. I think this is where more explorations of the data is useful. We're going to see later in the parameters, there's actually ways to drop some features, especially during training, and that's how I would suggest to do it. But we'll get to that later in the notebook. Another question: how does gradient boosting decide the split? So it's based on information gain. I won't go too much in the mathematics of it, but basically how much information, sorry for the lack of better words, but how much information is being gained at each node. And that can be defined in several ways. It can be, for example, like going back to that earlier decision tree I showed in the slides. You may remember the question was, will it snow tomorrow? And the first question was, is it a summer month? So for example, that is a huge information gain because it's simply just not going to snow as much in summer months. So I suggest reading more in terms of what information gain is, but that's the general idea. Can XGBoost be used for regression as well? Yes, so it can be used for regression. It's more commonly used for classification. As you will see, or as I mentioned, the leaf output is actually a score. and then it gets converted into a decision, like if it's less than 0.5 or higher than 0.5. So we're actually converting it into a binary decision. Someone said, in your opinion, what is the most useful importance type? I think given that our features have quite a bit of binary features, I think gain is better in this case, because it's very much directly on like how much the average gain caused by split. But weight is useful as well. I think it depends what data set you have. If you have a lot of non-binary variables, I'm sure weight is a good use. In the end, I think you should just you should check out each of them and see what you get. And I think from there, it'll be easier to see which one is more useful. Sorry, I'm reading through the questions. Someone asked, can we assume that this data set is balanced, or do we need to adjust it before applying ML? Yeah, as we saw in the earlier section, we have a 30, I think about 37% are canceled. So it is pretty balanced. So we don't need to worry about this for this use case. Someone asked, how is XGBoost fair with respect to other ensemble models, say random forests? I think, not to keep saying this, but it depends a lot on the problem. I think generally when you're working on a machine learning problem, you should try various models. You shouldn't just go into this problem being like, I'm going to use gradient boosting only. It's good to, you know, test out gradient boosting, definitely test out random forest, see if you're getting around the same accuracy. So I wouldn't suggest using one over the other for all types of problems. I really suggest trying out both and seeing what you get along with other machine learning models. Yeah, so someone asked, so to simply put, XGBoost is nothing but running decision trees multiple times if the base learner is a decision tree, and in each step improving it better than the previous version. Yeah, that's right. So it's not like a bagging method would be running multiple decision trees in parallel and then, you know, somehow averaging their output, while XGBoost is running decision trees sequentially. So they're not running in parallel, and they're taking the output of the preceding tree. Okay. Someone asked, when would be the right time to use XGBoost instead of the simpler decision tree? So again, decision trees are very powerful, very interpretable, but they are weak learners. So if you're working on more of a complex problem, then XGBoost is going to have better results. If you're, I think it's worth trying out on a decision trees when you start, you know, exploring the data, but XGBoost for more complicated problems for sure, because decision trees are known to be weaker learners, which again is defined as slightly better than chance. So someone said, will XGBoosting work well for sparse data? Not exceptionally, because a lot of XGBoost is decision trees. So you have nodes that are like, you know, is the lead time less than 5 or greater than 5? So what that means, if you have a lot of empty data, there will just be a lot of things that can't be classified. So it's not the best option for Someone asked, are the XGBoost and Scikit implementation of XGBoost the same? They are somewhat similar. XGBoost has some more memory, is better, is more efficient on memory. So XGBoost has something called dmatrix, which we won't touch on here, but it's very powerful if you have a large amount of data. So if you're working on a big data set, I recommend using XGBoost rather than Scikit Learn. That being said, you can pretty much adjust the same parameters on both. So I would suggest using XGBoost for big data sets. Someone said, when should we use XGBoost? I think it's a good tool to have in your toolbox. It's definitely worth trying it out for, I think, classification problems especially. You can use it for regression, but given the nature of decision trees, it's usually better for classification problems. I think it's also great, as I mentioned, if you want something more interpretable, if you want to present your results to someone and understand why, and also explain to them why the results are a certain way, then XGBoost is good, because you can really, as we see here, show the decision tree as well as the feature importance. Someone asked, what makes XGBoost extreme exactly? That's a good question. I'm not sure the origin of the name, but I think it's the fact that you're boosting, as I said, boosting is taking, is an ensemble method where you sequentially train learners, weak learners. I think the idea with Extreme Boost is you can have a lot of decision trees in one model, which makes it quote unquote extreme. So for example, you saw the default in Estimators is actually 100 decision trees, which makes it quote unquote extreme. That would be my guess. Can I use XGBoost if I have a large population, but only 0.1% of the observations have outcome of 1? There, I would recommend doing something with your data to have more of the minority class, have a higher percentage, like upsampling or something along those lines before using gradient boosting, because that is quite a low, 0.1% of positive instance is quite low. So I would definitely manipulate your data a bit there. And then this is a perfect question to segue into the rest of the notebook. Someone asked, are there any other hyperparameters of particular importance other than the ones you modified for this session? So I'm going to jump in now. Note there will be a Q&A session again at the end. So please keep adding your questions and I will hopefully get to them all. All right, so digging into parameters, there are many parameters for tree boosters. I'm going to open up. This is the documentation for XGBoost. You'll see it's linked throughout the notebook. Just really useful information here if you want to dig deeper. But I've selected about several parameters I think are really important to know about and that will hopefully improve our performance. So let me just get set up here. Okay, so the first is let's first instantiate a classifier, and this time let's do 25 boosting rounds instead of 10. I think 10 is not that much, so just to make sure we give our model a fair chance, let's upgrade that to 10. So again, we're going to instantiate from the classifier class. And then we're going to do n estimators equal 25. We'll do the eval metric again to error. This is something you can change as well depending on your problem. And then we'll do random state 1, 2, 3. All right. So the first one that we can change is MaxDef. We've already went over this, but the idea here is the higher or the more you make this value, the more complex the model will be, because there's just more in the model, more nodes. And as we know, the more complex a model, the higher the variance, the more likely it will overfit. So let's set this from 3 to 10 and see what we get. So we'll do XGB classify CLF dot set parameters and max depth equal 10. And then again, we'll fit the classifier. I'm gonna copy and paste this for the next one, so you're not seeing me type the same things. Y train, and then again, predicting using XGB CLF dot predict X test. And here you'll notice I imported accuracy score from the sklearn, so we don't have to keep calculating accuracy. And we can do that by the first argument is the actual values, which is Y test, and then our predictions. And when we get that, we get 83.67. I think our baseline was around 80. So that's already quite an improvement. It may be due to increasing the max depth in combination of increasing the N estimators to be 25. So another useful parameter is call sample by tree. And this goes back to someone's question about, do you want to use all the columns? So right now, when you create a, the default for this is 1, meaning that each time a tree is constructed, so every time there's a boosting round, it can take it from all the columns. What this does, it subsamples the columns for every tree that's constructed. So essentially, this lets us limit the number of columns used when constructing each tree, and each tree is going to get a random subsample. So if we set it to half, for example, each tree is going to get a random selection of 50% of the columns to build from. Why do we want to do this? Simply, it makes the model more robust to noise. So it forces the model to depend less on certain columns, essentially making the model less complex and more robust. So what I'm going to do here, so I'm not rewriting the same thing, essentially for each of these, we're going to be setting the classifier, setting a new parameter, and then fitting it, and then retraining it. So here we'll just do call sample by tree, and we'll set that to 0.5. So we're taking 50% of the columns. And then here we get 83.7, so slightly better than before, which is interesting. Maybe this is preventing our previous model from overfitting too much on the test data, on the training data, excuse me. So another thing to note about call sample, this is really popular to make XGBoost more robust. There's also different ways you can sample. You can call sample by level. So now if you have a tree, for each level, there's a different sample of columns. So this is different from the whole tree. That's making it even more, adding even more randomness. And you can even do it by node. So each node would have a different subsample of columns. Then we also just have subsample, which is basically the same idea as for columns, but this time for rows. So it's a subsample ratio of the training instances. The default is 1, meaning that each tree gets all of the rows, but we can, for example, set it to 0.5, which would mean that XGBoost randomly samples half of the training data prior to the next tree. This is useful for preventing overfitting because it's forcing different parts of the data, while instead of having each tree focus on 100% of the data. So let's try setting this to 0.75. Again, that means that each of our trees will get us random sampling of 75% of our data. Again, what we'll do here, excuse me, is change subsample. Is there an underscore there? to 0.75. Okay, so we don't see much of a difference here. I'm not actively trying to improve the performance right now, more so showcase the different parameters here. We'll get into hyperparameter tuning after this section. Then we have gamma. I think this is a really good one. It's just to help make your model less complex, so less chance of overfitting. The idea here is that you want to make sure that, let me start over. The idea here is that you want to, gamma represents the minimum loss reduction required for a node to split. So here we're saying we want to be more conservative about how we split our tree. If we feel that it's not meeting a threshold of gain, then we shouldn't split it, and that should end the tree. So increasing gamma means less splits, meaning less complexity. So the default is 0, so that means gamma isn't activated, and the nodes always split until the maximum depth. We're going to increase it to 0.25 for our case and see what that does. This is taking a little bit of time to run, which so for some reason, sorry, the cell is taking a bit longer to run. In the meantime, I'll move on to learning rate, and we'll come back to that cell. So learning rate, if you've done machine learning, this is probably a parameter you've heard of. Learning rate affects how quickly a model learns. So gradient boosting, we know, works by sequentially adding weak learners to the model. Each new weak learner attempts to correct the residual errors from the preceding trees. This makes the model very susceptible to overfitting compared to other models, because we're really trying to correct the errors of a previous tree, which can cause the model to just memorize the data, essentially. So learning rate can really help that slow down by shrinking the resulting weights of the current tree before passing them on to the next tree. So the learning rate of our model defaults to 0.3 in XGBoost. We're going to change it to 0.1. And there's an important thing to note here. The learning rate and the number of trees should be tuned together. If we decrease the learning rate, we need to make sure there are enough trees to learn something and avoid severely underfitting. So therefore, a lower learning rate will require more boosting rounds. That's something to keep in mind. We're going to see this in regularization as well, that the different parameters will play into each other, especially the number of boosting rounds and the number, how deep your trees are going to go. So this is running a little bit, so I'm going to run so I'm going to run all above and see what happens. Just resetting the notebook a little bit. Let's see if the earlier cells are outputting. No, they're still running. Okay, so I think something's up with the notebook. I'm just gonna refresh this page. Sorry about that. right. So let me go back to where I was. We were just talking about gamma, and I'll run. Yeah, I'll run from the beginning. Run all above selected cells. So let's see. All right, so there seems to be an issue on our end. I'm so sorry about that. I'm gonna keep going throughout the notebook, and I'll add the code in, and you guys can try running it on your side, but I'll keep explaining the parameters. So before we go on, let me just set the learning rate here. We want it to be at 0.1, but again, same thing here. We're just training it and then predicting, same as we've been doing. Okay, and then another important one is RegAlpha. So now we're going to talk about regularization. Regularization is known in machine learning to prevent overfitting. So there are two popular ones, L1 and L2. Both are available on XGBoost. L1, as a refresher, is lasso regression, and it aims to reduce overfitting by discouraging complex models. So a lot of regularization and avoiding overfitting is just discouraging complex models. We've seen this in the learning rate in gamma as well, and it's a theme that you will continue seeing. So in the case of gradient boosting, L1 does this by adding penalties on leaf weights. So increasing the L1 regularization, also known as RegAlpha, drives base learners' leaf weights towards 0. So the default is 0, meaning there is no alpha regularization in our model currently. And we can activate it by simply putting a value other than 0. L2 is another big regression method, also known as ridge regression. It's available in the parameter reg lambda. It's known to have a smoother penalty than L1. This means leaf weights smoothly decrease rather than going directly to 0, so there's less risk of sparsity. So make sure to try out different regularization techniques. L1 isn't going to be, going to solve every problem you have. It's really trying out different ones here. So let me see if there's any progress on this notebook. I'm gonna run here. Okay, it seems to be working. Let me see if I can run where we left off. Okay, there we go. We're back. Sorry about that again. So here, I think I didn't run this gamma cell, but again, I'm not actively trying to improve performance, just showcasing the different parameters, gamma, learning rate. Let's see what happens here. This one actually lowered our accuracy. Again, we only have 25 boosting rounds, so increasing or decreasing learning rate was maybe not the right move here. We also have RegAlpha. Let's try that out and see what that does. I'm gonna copy and paste again. And then oops. Yeah, 82, this didn't do much actually, just barely changed. And then, yeah, so we've covered a few parameters. Again, we can print them out here. Oops, that's typo on my end. And then when we get that, again, we see all the parameters and the things we've changed, like gammas here, co-sample by tree. We can see that by node, by level, which I mentioned before, that's still set as 1. Learning rate, MaxDef. There's a lot more here, min child weight, the alpha, lambda. So this is sort of overwhelming. You know, you have all these different parameters. They all play with each other and affect each other. How can you possibly find the right combination? You can't manually try them out like I've been doing here. This is not the way you should go. So that's where hyperparameter tuning comes in. If you've done machine learning before, I'm sure you're familiar with hyperparameter tuning. There are two popular methods for doing this. I mean, there are many, but the two most popular methods are grid search and random search. So grid search can get really computationally expensive because you're searching over a large hyperparameter space. And by hyperparameter space, I mean, think about all these different parameters and all the different combinations you have. So if you have even like 4 parameters that's with different values for each, you can get a lot of different combinations. So your hyperparameter space becomes huge. So because again, this is a live code along session, I don't want to spend 30 minutes training this and going through grid search. So we're going to use random search because it doesn't try all the hyperparameter values. Instead, it tries a fixed number of hyperparameter settings that we can actually set ourselves, and then we can tell it how many combinations to try. So here we're going to use scikit-learn's random search cross-validations. And what you need to know here is it takes in the following arguments. It takes in the estimator. In our case, it's going to be the XGB classifier. It takes the param distributions. So unlike params, which is what we've been playing with before, this is the distribution of possible hyperparameters to use. So we're going to define this here in the parameter grid. I've selected a few parameters to try out. As I showed you above, there's a bunch of others we can try out. I'm only keeping it at 5, but if you're going to keep doing this at home, you can add as many as you want here, even the ones that we haven't covered. Another thing it takes is CV, number of cross-validation iterations, because it's using cross-validation. And iter here is the number of hyperparameter combinations to choose from. So unlike grid search that tests out all the possible combinations, random search, we can tell it to choose a set amount of combinations. And then we're also going to use verbose, which just prints out more output for our sake to just understand where the model's at in tuning. Okay, so let's first define our parameter grid. As I said, I've picked 5 parameters to focus in on: MaxDef, alpha. So we have some regularization going in here, subsample, learning rate, and number of estimators. So there are a few different ways you can define the distribution of a parameter. I'm going to show you a few here. So the first is MaxDef. In this case, let's say we just want values from 3 to 12. We can simply do list range 3 to 12. So that's just going to be an output of all numbers between 3 and 12. And then for alpha, we want a specific set of 4 values. And here we can simply just create a list with 0. This is 0.001, 0.01, 0.1. And then we have subsample. Again, we just want to do a range of values here. We can do subsample. Oops, sorry. 0.25, 0.5, 0.75, 1. We also have learning rate. So here, another way you can do it is, let's say we want 10 values equally spaced between 0.01 and 0.5. Instead of typing it out on list and figuring out what those exact values are, we can use a NumPy function called linspace, which we put in the starting point 0.01, the end point 0.5, and we want 10 values between those, equally spaced. So they're not randomly chosen. And then we have n estimators. Again, that's the number of boosting rounds. Let's do 10, 25, 40. Okay, so now that we have our parameters set, oh, let's see, I forgot. Oh, something's going on. Okay, maybe it's fine now. I forgot the commas here. You can tell because this red parentheses is angry at me. Let's see. We can instantiate the XGB classifier. This is the model we're going to be putting into the randomized search. Again, we want to set the eval metric as error. This is something you could put into parameter grid if you wanted to try different types of evaluation metrics. And then you can set the random state. Again, I'm going to set this at 1, 2, 3 so you can get the same results as me if you want to reproduce that. Sorry about this error message. Where was I? So now we want to instantiate the actual random search. So we'll call this XGBRS. And then we'll call randomized search. Ooh, I did not spell that right. Randomized search CV. The estimator, so that's the model we want to try out with different parameters. That's going to be XGBCLF, what we just defined. The param distributions is going to be RS params grid, param grid right here. And then we need to define CV, so that's number of cross-validation iterations. That's usually 5. I'm going to put 3 here so we don't spend too long in training. And iter is the number of hyperparameter combinations to choose from. So I'm going to say pick 5 and let's see what does the best. Verbose, I'm going to make that 2. That doesn't change anything in the model. It's just the model output as a training. So if you want to keep track of where your model is, that's useful, but it's not going to affect your results. And then again, random state 1, 2, 3. And then now we fit the data. Let's try it out. Okay, and then how this works to print the best accuracy. Say, for example, we want to print first the best parameters found. We do XGBRS, so we're calling the randomized search object, and we're going to say best params. So that's going to output that, which we'll see in a few minutes. And then we're also going to do print best accuracy found. And that's going to be, again, calling XGB, sorry about this message, XGBRS best score. Okay, let's see if that runs, if I didn't have any typos. Okay, yeah. Typo here. Let's see what's. Oh, I'm forgetting parentheses. I knew something was up here. Yeah, okay, this should run now. All right, so let's see. This is because I put verbose as 2, that's why it's giving me some output here. Again, it's useful. So it's fitting 3 folds for each of the 5 candidates. So that's going to be 15 in total training. And we see that here. So for example, it randomly chose to first do MaxDef equals 4, 25 estimators, subsample is 0.75 with a learning rate of 0.1733, which I assume is from this, you know, this will calculate 10 equal values between these 2 values. So we see here that it indeed does through 3 folds for each of the 5 possible combinations. And we got the best parameters we found is 0.5 for the subsample, and estimators equals 40. MaxDef equals 9, learning rate 0.227, alpha 0.01, and then an accuracy of 83.43. So I think the accuracy of this can be much more based on what we're seeing here. Again, I'm trying to limit the amount of training we're doing in this code along, but what we see here is already that when the estimator is 40, we're getting better results. So what that means is that if I were to redo this again, I would be interested in putting higher values here. And then also MaxDef equals 9. That's interesting. Maybe 3 is too low to start with. We should start it at 5 or even 8 and see go up to 20. Again, it isn't a precise art here. It isn't precise. It's more of an art. So there's a lot we can try out here to keep improving the accuracy. Okay, so right on time, I'm going to move on to some questions, and let's see what we have here. Okay, so someone asked, does MaxDef of range 312 give values from 3 to 11? I think it gives 3 to 12, but we can easily check that. Let me just run this and see what we get. Oh, actually it runs 3 to 11. So my bad here. This is 3 to 11. It doesn't include the maximum cap. So thanks for asking that question. Good point. At the beginning of the analysis, overfitting to the data and after regularization of the XGB can be a strategy. I'm not sure if I understand this, the question, but basically what we did here is first we did a baseline accuracy where we probably overfitted to the data, and then we tried to improve it using regularization methods. So I think it is a good strategy to first, see what you get and then see how much you can improve it. Usually after putting some regularization techniques, you'll have a better idea of how much you were overfitting in your baseline, for example. Someone asked, when or how do we know when the number of boosting rounds are more than what is required, resulting in overfitting? Yeah, so this comes back to you're going to have to do some hyperparameter tuning. Here, you can try different distributions for the number of boosting rounds. I think it's important to use cross-validation as well to make sure you're getting a better picture of what accuracy is. So the number of boosting rounds is going to depend on the data set. I mean, I think it is pretty telling that the default is 40, so you do want quite a bit of them. We have been pretty conservative in the number of boosting rounds we have used, but it's a lot of playing around and tuning. You mentioned that more complex models, deeper trees tend to overfit. Are there any specific techniques to handle overfitting in XGBoost? So yeah, deeper trees, many trees. So limiting how deep trees can get and the number of trees is a great place to start. And then adjusting learning rate and applying different regularization techniques will be useful as well. Okay. Alex, someone posted a question. How does XGBoost performance compare with that of deep learning models? So because decision trees are based on nodes, it isn't great, for example, for image computer vision or NLP. So you would definitely want to use deep learning for that instead. That being said, XGBoost has shown to have performance comparable to deep learning. One of the reasons the XGBoost library got so popular actually was because a lot of people were using it to win Kaggle competitions. So it was seen as a very effective way to use machine learning without necessarily using a deep learning model. So I think it's worth trying out, but I think for more complex human tasks like NLP computer vision, you definitely don't want to use XGBoost, but it is worth using it for problems where, especially classification problems where you do have quite a bit of features to work from, like our data set. We had 52 features. So someone asked, how do we use the early stopping rounds in XGBoost to stop overfitting? So this is something I didn't get a chance to go over in this notebook, but early stopping rounds is a useful tool. So what early stopping does is usually a tree stops training, or a tree is complete once the max depth is hit. But early stopping basically says, actually, let's stop this tree when the information gain stops being as useful. So instead of waiting for the tree to build out to the max depth, we're cutting it based on a threshold and saying, actually, this tree is more depth is not going to give us as much information as we want. So we can just stop this tree here and move on to the next one. So that is a useful one to use overfitting because it's another way to minimize the amount of levels you have in your decision tree, making it less complex. Okay. Let's see what other questions we have. Someone asked, should we use L1 and L2 regularization together? You can, but again, I think an important thing to note about regularization rate is it depends on how many boosting rounds you have. So if you have not that many, you don't want to give too much, you don't want to put too much regularization, otherwise the model simply won't learn because it's not getting a chance to. I think it's something worth trying out when you're hyperparameter tuning, but also keep in mind how it's affected by the number of trees you have. Someone asked, typically, how much longer does grid versus random search take, and is grid search improve accuracy considerably? Yeah, so if you have the time, grid search is great. There are other search methods that are more efficient, but grid search does take longer than random search because grid search will test out all combinations, while in random search, I tooled it to only try out 5. So I was able to control how long it would take, but it's definitely not as thorough. So for example, it didn't try out like a depth of 11 with, the other possible combinations. So I recommend grid search, but you also don't want it to run on forever. So random search is nice. Maybe you can increase this to be like 25 instead of 5, and you can get a bigger picture of which combinations are working, and then from there decrease your parameter space, and then you can use that to decide what distribution you want for grid search. Yeah, generally that's something I would advise, is starting with random search, making sure you have enough. I don't think 5 is enough. Seeing what's working the best, and then using that to make a smaller range of values here and putting that into grid search. Because if you see here, we have quite a bit of range here. We're trying 3 to 11, 10, 25, 40. It would be interesting to, if we know that we need at least 40 trees, then we could do something like 40, 50, 60, or even more, for example. Okay. And I think that's all for today. What I will leave you with here is, as I said, there's a lot to try out at home. I don't think this is the best accuracy you can get. So I encourage you to try out Workspace and see how far you can get in terms of accuracy. Add more parameters in here, change the distributions, add more iterations, maybe improve the cross-validation. You could even try grid search if you wanted to. So see the best accuracy you can get, and then publish and share your results on Workspace. You can also send it directly to me by email or through LinkedIn. But thank you so much for attending, and have a great day.
Thank you very much, Liz, for your great presentation, and thank you all the attendees for your participation. I'm going to put a survey link in the chat right now as we speak. Your feedback will really make a difference for improving the future events that we hold and to improve Workspace for you. So this rounds up the 6th Workspace live code along. The session was recorded, and we will share the link to the recording via Slack, email, and social media. We will also share this notebook with you and the solution that Liz prepared. With that being said, we will leave you to it, and I hope you all have a great rest of your day. Bye-bye.